According to work energy theorem, the increase in the kinetic energy of a moving body is equal to dash by a force acting in the direction of moving body. So of course, if the kinetic energy is increasing, there must be some work done on it. That is what the work energy theorem is. Work done is equal to change in kinetic energy. And if it is force is in the same direction of moving body, it'll be a positive work done. So the kinetic energy will increase. That's why the word increase is used here. Let's go to the next question. A wire clamped at both the ends is stuck in the middle. It will possess vibrational kinetic energy. It can't be rotational. It can't be translational also. For example, if this cursor is there and if I say I want to translate it, this is called translation, moving one point to another point, changing positions. And if it takes some angle, let's say I'm not able to rotate this, but you can get the idea, like if it goes like this, I will say it is rotating, it is having rotational kinetic energy. But the string, like in guitar string, it doesn't go anywhere. It doesn't rotate, it vibrates. It does to and fro motion like this. If you take any point of the string, it's just going back and forth, back and forth. And that kind of energy is called vibrational kinetic energy. The velocity of a moving cart is reduced to one third of its initial velocity. Its kinetic energy is reduced by, so we can directly by intuition we can calculate this, but we should know the formula of kinetic energy and velocity. The relation is kinetic energy is half mv square. So only velocity has been reduced. And if you see the relation is of the square of the velocity. So kinetic energy is related to velocity by its square. So if it is decreasing by one third, kinetic energy will feel it by the square or 1 by 9. So that is why the answer intuitively we can give as option D. But if we want to solve mathematically, this is how we will go. Let's say Ki initial is half m1 v1 square and K2 is the final kinetic energy half m2 v2 square. Mass they have not given, so let's say it is constant. Mass is considered same. Let's say it is m only, m1 m2 is equal to m. But a v2, the final velocity is one third of the v1. So let's say if we put this in K2, what will happen? So K2 will be half m into v1 by 3. v2 is one third of v1, so we can put that value here. So v1 by 3, now if you square it, 1 by 9 will come. I can take it outside and I'm keeping this half mv square expression close, half mv1 square. Why? Because half mv square, I know what is that. That was the initial kinetic energy. So I can say the final kinetic energy is 1 by 9th of the initial kinetic energy. So this way, mathematically also we can prove. By intuition, we can go how they are related, how kinetic energy is related to velocity, and that way we can calculate also. Let's see this question. A body of mass 10 kg is moving with a velocity of 20 meter per second. Mass of the body is doubled and velocity is halved. Its initial kinetic energy is. See how cleverly they're asking about initial kinetic energy. I thought because mass is doubled and velocity is halved, they will ask for final kinetic energy, but they are asking for initial, right? So remember to read the question properly. So the initial kinetic energy will be coming from this statement. Put 10 kg here, half mv square, and 20 squared, you will get 2000 joules, which will be the answer C. Right? So the catch was they were asking just initial kinetic energy. This other data was just given to confuse us or to test us whether we are reading the question properly. Okay, let's go ahead. On doubling the velocity of a moving body, the quantity which gets doubled is like it is increasing or decreasing with the same expression, like P is equal to mv. This is momentum. So momentum is directly proportional to the velocity. It has a linear relation with the velocity. Nothing like kinetic energy as we saw in the previous case. Kinetic energy is related to the power of 2 of velocity. That is not a linear relation. In this linear relation, how much the velocity will increase or decrease, the same way the momentum will change. So if the velocity of moving body doubles, the momentum also doubles. Kinetic energy is not related directly, so that will not happen. Okay. And acceleration is a rate of change of velocity. It is not the velocity doubling it. Acceleration, we have to think about how much time it will take also. So acceleration is also a different thing here. Weight also a different thing here. Weight has nothing to do with the doubling the velocity. The car, if it's moving with a higher speed, doesn't mean its weight will change, right? So the momentum is the only quantity here which will be doubled or have the similar effect as velocity. In a photoelectric cell, the change in energy is from, so it is light energy to electric energy. So this is a solar cell I've drawn. This is the light we capture, and this solar cell, what it does is it converts this light energy. It takes energy from the light and then it converts it into the electrical energy, so that the solar lamps you must have seen, so that can be glown. So the answer is option B. In a petrol vehicle while in motion, the change in energy is from. So when it is in motion, it means engine is working, engine is burning fuel, and what is fuel is chemicals. So the chemical energy is getting converting into heat energy, right? That's why we are getting pressure on piston, and then it is translated to the wheels. So we can say the option B will be the correct answer, chemical energy to kinetic energy. Let's say question number 8. The nuclear fission. Fission means to break. What happens? Chemical energy changes to electric energy. No. Mechanical energy changes to chemical energy. No, we can't say that. Nuclear energy changes to electrical energy. This is the right way to say. Chemical energy is like burning of petrol engines. But that is not a nuclear energy. Nuclear fission, we break the nucleus. That is what we are talking about, making different bigger atom into smaller atoms, and that way we are getting energy out of it. So that will be called nuclear energy, and that we converted to the heat energy. Then we warm up the water with it, steam we generate, and then we move the turbines, and that gives us electrical energy. But here we will say the option C is the correct. In between what happens they have not mentioned, but this C option is better answer here, so the answer will be C. So this is, I have written here, nuclear energy will get converted into thermal energy, then gets converted into mechanical energy, and then gets converted into electrical energy. But in this question, only this part extremes were given, not these middle ones. Okay. Force F applied on a body moves it through a distance S along F in the same direction. The energy spent is just a multiplication F into S. So see if it is our formula is F dot D or FD cos theta. Cos 0 degree because they are in the same direction along F. So we will get 1 or we'll get the simple multiplication. So it is option A. In which case will the potential energy decreases? If we compress the spring, no, it will store the potential energy. The potential energy will increase in this case. Stretching a spring, again we are pumping in the potential energy. It will try to come back. Moving a body against gravitational pull. What does that mean? That means if, like, for example, this cursor or this black thing you are saying, it is if it pulls it up against the gravitational pull, then are we decreasing potential energy? No, we are increasing its potential energy because the height is increasing, right? So the only option left is D, but let's read it. A bus descending down a steep hill. So when a bus is coming, like it's going, let's say, going like this, bus, and when it goes downhill, so its height decreases, right? So its potential energy also decreases. So the D will be the correct option in this case. Think of a bus as we are lowering the mass. So if we raise up, if think about this a ball, then if we are putting on this building, like roof, then we'll say the potential energy had increased. And if we lower this ball here, 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 then what will happen? We'll say the potential energy has been decreased. So that is what is similarly happening with the bus. It is descending, coming down. So it will be the decrease in potential energy. Okay. A light and heavy body have equal kinetic energy. Which body will have a greater momentum? So now there is a relation between kinetic energy and momentum. There is a relation, and we can very easily, if you don't remember that, we can easily derive it. We know K is equal to half mv square. We know momentum, I'm denoting it by P is equal to mv. So we can say V is equal to P by M. V, I'm taking this M here. Now, if I put instead of V, P by M here, I will end up having this half P square by M, or P square will be equal to 2mk. 2m, I'm taking other side here, this side was K. So P will be the square root of 2mk. So what you can say here, if kinetic energy remains same, the light and heavy body have equal kinetic energy. So the kinetic energy is same, which body will have greater momentum. So if this thing is same for both the bodies, only the difference which can be made is by this, the mass. So the lighter body will have less momentum, and M is more, then it will have more momentum. So seeing the relation, we can get the answer right here. So the heavier mass, heavier mass will have more momentum. So that way we can understand this kind of question. This needs to have derivation if you don't remember the formula, or if you remember the formula like P is square root of 2mk, and find what is constant, forget that, and what is remaining, you can relate how M is related with P. And with that, you can tell, like, if mass reduces, what will happen? Momentum will also reduce. If mass increase, then momentum is also increase. So that way we can answer these kind of questions. Let's say question number 12. Okay, it is assertion based question. Let's have a read. If momentum of a body increases by 50%, its kinetic energy will increase 125%. Now, how to test it? So we should know the relation between kinetic energy and uh, the momentum. So we have already driven it here, where it is. Yeah. So see, P square is directly proportional to K, we can say. So now what we are assuming, let's say mass is constant. Okay. So they are saying this momentum is increased, and they are asking kinetic energy. Let's see if that relation is true. So kinetic energy is directly proportional to P square, that we know. So if momentum is increasing by 50%, what does that mean? 1.5, right? 50% is 1.5, 90% is 1.9. So if momentum becomes 1.5 into P square, let's say, so 1.5 square will be 2.25 P, right? So 2.25, what does that mean? It means increase of 125%. So think about, whenever we are getting fraction, we should be able to think in terms of percentage. So when I was saying 50%, we have to it should come in our mind like it is 1.5. And if we are getting 2.25, so kinetic energy has increased 2.25 times. What does that mean? It means it is 1 minus 2.25 minus 1, that is 125, 1.25 increase or 125% increase. So that way we just need to understand how fractions and percentage are taking care. So assertion is true. Kinetic energy is proportional to the square of the velocity. We cannot say directly, but I think in your book they have said it, because they are taking, because P is equal to mv. So then momentum, we will say, we will put it here, then we can say kinetic energy directly proportional to the velocity. So you can take option A as the right answer for this question. Let's go ahead. Assertion. A spring has a potential energy in both cases, whether it is compressed or stretched. True. That is true. See, if this is the normal spring length, and if we, stretch it, so the external force shown by Fe will be in this direction, and the spring will start opposing it. It doesn't want to get stretched, so the force will be like this, right? So it will have that potential energy. uh, and if even in the case of we are compressing it, the swing force will act on the opposite side. So again, we will have the potential energy. This is because work is done on the spring against the resulting force. Yes, that's what we are doing. See, if we are stretching it, we are doing force against the spring force. If we are compressing it, then our external force is this side towards the left, but the spring force is this side. Again, we are acting, working against the force of spring. That's why its potential energy is increased. So both A and R are true, and R is the correct explanation of A.